Ever wonder how scientists predict whether patterns or model fluid flows with just a few sensor readings? Today, we're diving into a groundbreaking AI method called FunDPS, a game changer for solving complex scientific puzzles. Let's break it down. So what's the challenge? Imagine trying to solve a jigsaw puzzle with most pieces missing. That's what scientists face with inverse problems, figuring out hidden details from incomplete data. Think of it like guessing a recipe from a single bite, or reconstructing a damaged painting from a few brushstrokes. Traditional methods struggle here. They're like using a ruler to measure a mountain, rigid, error-prone, and stuck in a fixed grid. Enter diffusion models, the digital detectives of AI. These models work by reversing a process where noise is gradually added to data, learning to undo that noise to generate realistic outputs. Think of it as sharpening a blurry photo step by step. But here's the twist. Researchers are now using these models to tackle inverse problems in function spaces, a fancy way of saying they're solving equations that describe real-world phenomena, like fluid dynamics or heat transfer. The key innovation. FunDPS treats solutions as continuous functions, not just grids of numbers. This means it's resolution independent. It adapts whether you're working with low-res data or high-res simulations. Imagine a painter who can switch between sketching on a napkin or a giant canvas, the same creative process, no matter the scale. How does it work? FunDPS uses a pre-trained diffusion model as a prior, like a library of known patterns. When faced with noisy or sparse data, it combines this prior with measurements to generate the most likely solution. It's like having a smart guesser that refines its ideas as it goes, guided by real-world evidence. But here's where the math gets cool. The researchers extended a classic formula called Tweedie's formula to infinite dimensional spaces. This gives the model a mathematical shortcut to estimate the most probable solution, even when data is scarce. Think of it as a GPS that adjusts your route in real time based on traffic updates. The results? FunDPS is 25 times faster and 32% more accurate than existing methods. It uses a multi-resolution strategy, starting with low-res data to grasp the big picture, then refining details. This cuts computation time by 75% without sacrificing precision. In tests, it reconstructed complex systems like fluid flows from just 3% of the data, outperforming competitors. So why does this matter? From climate modeling to medical imaging, solving inverse problems faster and more accurately could revolutionize science. Imagine a single model trained on physics equations that adapts to tasks like predicting earthquakes or reconstructing MRIs from sparse data. The possibilities are endless. Thanks for watching, stay curious, and let's keep unraveling the mysteries of science together. Ever wondered how AI can turn random noise into realistic images or solve complex puzzles? Today, we're diving into the math behind one of the coolest techniques in machine learning, diffusion models. Let's break down how they work, step by step, and uncover the theory that makes it all possible. Imagine you're trying to reconstruct a blurry photo. You start with a completely noisy image and gradually remove the noise, step by step, until you get a clear picture. That's basically what diffusion models do, but with math instead of a photo editor. Here's how it works. The model uses a noise scheduler that starts with the highest level of noise and slowly reduces it to zero. At each step, it takes the current noisy image, runs it through a neural network, the denoiser, and gets a guess of what the clean image might look like. Then, it adds a little more noise to simulate the next step in the process. This back and forth continues until the noise is gone, leaving you with a realistic sample from the data distribution. But here's the magic. This process isn't just random. It's based on a mathematical framework called diffusion posterior sampling, which uses a deterministic method inspired by Euler's second-order algorithm. Think of it like a guided journey through the noise, where each step is carefully calculated to get you closer to the final result. Now, let's talk about the deeper math that makes this possible. The researchers behind this work had to tackle a tricky problem: how to connect noise removal with probability theory in infinite dimensional spaces. They turned to something called Tweedie's formula, which links score functions, a measure of how a probability distribution changes, to conditional expectations, the average value of a variable given some information. But instead of working in regular spaces, they generalized this to Banach spaces, a type of mathematical structure that's super flexible and can handle infinitely many dimensions. Imagine you're trying to predict the weather. Normally, you'd look at a few factors like temperature and pressure. But in complex systems, like climate models, you have infinitely many variables. Banach spaces let mathematicians handle these scenarios. The key insight here is the Cameron-Martin space, which identifies the directions in which you can shift a probability distribution without breaking its rules. It's like finding the right path through a maze of possibilities. Their proof showed that when you add noise to a distribution, like mixing salt into a soup, you can reverse engineer the original distribution using these mathematical tools. This isn't just theoretical. These ideas power modern AI systems that generate images, solve inverse problems, and even crack encryption. By understanding how noise and probability interact in abstract spaces, we're unlocking new ways to tackle problems that were once thought impossible. So next time you see an AI-generated image or a solved puzzle, remember, it's all built on this elegant dance between noise, math, and probability. Thanks for watching, stay curious, and we'll see you in the next video.